Hi, everyone. No. This is our last time together until the final exam. So we're in week 13. And as you know, things have really spread up over the last few weeks, right? So keeping you on your toes and keeping you busy. You will see, as was pointed out, Ariana said, hey, the due dates have kind of been extended. So I've opened those up till the end of semester to give you time when you have time to complete them. But don't just complete them all on the last day after you've written the exam. They're helpful for practicing for the exam, but I want to give you a little bit of freedom with it. So today we're going to do three rather big things. We're going to learn about integration, which is the opposite of taking derivatives. So we're going to reverse the derivative process. I remember mentioning to you early on that at this point, when we're doing integration, that we'd be really looking mostly at power rule and exponential rule, so nothing too awful or really too challenging. So we're not going to look at reversing quotient rule or chain rule or product rule or anything, okay? So that will be a relief to you. We're also going to look at two uses of integration, and that's the area under a curve, and you'll see how that will serve us in some great business contexts. And the last thing is producers and consumers surplus. Okay, any questions before we start about this or about anything that we've done up to now? Are we all right? Yeah? All right. So when we talk about integration, I want to actually get you to think about how we take derivatives. So I'm going to show you a series of functions, and I want you to tell me what the derivative is that you would think, right? So if I had a function f at x is equal to 3x squared minus 7x plus 14. I need to make this smaller. What would be the derivative of that function?
6x minus 7.
Okay. So we have 6x, minus 7, yeah? Okay. So what if we had this function? We have 3x squared minus 7x minus 0.6. What will be the derivative of that function? The same. Okay. All right. What if we had this function? Three x squared minus 7x minus 3/4. What would be the derivative of that function? It would be the same. Okay. So, do we agree it would be the same using power rule, right? And we have the constant rule at the end. So the question bodes then, if we are now today going to go backwards, if we're going to have the derivative, 6x minus 7, and we go backwards, how on earth do we know if we're looking at 3x squared minus 7x plus 14, 3x squared minus 7x minus 0.6, or 3x squared minus 7x minus 3/4? How do we know? How do we know? Well, what would we need to have in order to determine what that constant is? Do you have any idea, Dalmika? Sorry? A variable. Yeah, that's a good thought. How about a point, like a value of a variable? What if we had an x and a y value, right? So if we were given an x and y value, once we integrate the function, then we could use an x and a y in order to determine what that constant is, right? So that could help us. And that's going to be your definite integral where you've got to find the constant, yeah? when we look at area under the curve, we won't need to find that constant, and I'll explain why when we get there. Okay? Any questions about that? Are we ready to kind of do an integration, see what it looks like? Okay. So the first thing we would look at this question is, well, how do we know when we're given this function? Are we given a function? Are we given the derivative of a function? Like, how do we know? And just like we maybe. Okay, so just like when we started to find derivatives, remember we were looking for those words and I created kind of like a word wall, right? We had the words marginal, we had the words rate of change, we had depreciation, like we had a bunch of words that we equated with finding the derivative, right? So now we're going to see those words actually in the question referring to the function we're given. Okay, so we have this question now. It says imports in billions of dollars from country A have changed at the rate of, right? At the rate of. That's our key word right there that tells us, oh, okay, that's the derivative. That's the rate function, right? That's the derivative of this function. Okay. So that tells us that we do not have the original function, we have the derivative function, and then we can proceed and determine what they're asking us to do. So it says X is the number of years since 2000, so we know how that works, right? X is 0 for 2000, that's our baseline year. It says country A imported 222.94 billion worth of goods in 2001. It says find a function that gives the value of the imports X years after 2000, and then what was the value of those imports in country A in 2003. So why does it say country A imported 222.94 billion worth of goods in 2001? Yeah, it gives you that point, that X and Y value, right? So in that case, what will be the value of X? What will be the value? Just 1? Yeah? 1 and then 222.94. So we're not going to use that right away, but we're going to set it aside and we're going to need it, recall it later on. Yeah? Okay. So when it says find the function giving the value of the imports, that means find the original function, right? Not the rate of change of the number of imports, but of the value of imports, but the actual function. So that means we're going to reverse the derivative process. So we look at the function we have, the derivative function, and we go, okay, well, 0.18 x squared plus 0.24x plus 11.76. We look at those three terms and we say, well, it's power rule or, well, constant. We have a constant at the end, but it was power rule that got us there. And so I'm going to put a little reminder, power rule, x to the n. The derivative is n, x to the n minus 1. Okay. But now we're going this way, right? So instead of subtracting 1 from the derivative, to reverse it, we're adding 1. And I'm going to say that when you actually add 1 to the exponent right away, it signals something else. Hey, Brian. Okay, so we have g at x is equal to, so x squared in the original function used to be x cubed, right? So if I write x cubed here, that signals to me that 0.18 used to be some number multiplied by 3. So to reverse it, we're going to divide by 3. Yeah? So 0.24x, that's x to the 1. In the original function, it must have been x squared. Again, it signals to me that 0.24 resulted from some coefficient multiplied by 2. So now to reverse it, we divide by 2. Okay. 11.76, well, it has no x. It has like an x to the 0, actually. And so 0 plus 1 is x to the 1. Yeah, that's the original function. If you want to test yourself, take that and now find the derivative of it. And if it matches the derivative you're given, you can go, okay, yeah, I got this. So then what we're going to do is simplify, right? 0.06x cubed plus 0.12x squared plus 11.76x, okay? So that is the function that gives the value of imports x years after 2000, yeah? So B part just says, okay, well, now you've got that function. Can you now tell me what the value of the imports of country A were in 2003? So our baseline year, right? X is 0 for 2000. We've done this since the very first week, so this is something we're comfortable with. So X is 3 for 2003, yeah? Anything else we've missed? What have we missed?
First derivative?
No. The constant. We've missed the constant. Plus C. Plus C. Right? So now we have to find what the value of the constant is using that point. Remember we had that point, 1 for x, 222.94 for y. So we set it up. Okay, plus C. And then what you're going to do again is,
Do we
you
do
know,
11.6 times x,
which is 1.
which is 1? Oh,
Yeah, yeah. I left it out, sorry.
Yeah, no, that makes sense.
And then I'm going to do your exponents first in this case because x is 1. It's a bit of an easier example. So I have 0.06 I subtract from the other side of the equality. I have 0.12 and 11.76. And then I'm going to be able to find out what the value of the constant is. So. Well, if anyone finds that. So you're going to, 1 times 1 times 1 times 0.06, 1 times 1 times 0.12, 11.76. You can add them all up here and then subtract them from 222.94. Yeah. And so you'll get the value of C. Which is what? Anyone? Pawan, have you got your calculator with you?
No, I don't bring
Would you like my calculator to borrow? Got all the right answers in it?
Yeah, it's kind of too tired to do stuff paper.
Alright, no paper.
Paper.
Uh-oh. I don't know if I have any extra paper.
No, I'm good.
Alright. So what's the constant?
211.
211. Okay, so 211 equals the constant. Now we put that function back together. 0.06x cubed plus 0.12x squared plus 11.76x plus 211. Okay, now we're ready to substitute 3, right, to find out what the value of the imports were in 2003.
Is that what B was asking us?
Yes, yep. Bless you. I think we all need to go into our quiet corners for a couple weeks and come back feeling rested and healthy. Okay,
274.36.
what is it, sorry?
274.36.
274.36, anyone confer or agree? Anyone? Oh. Hope we got all our signs correct, yeah, plus, yeah. Okay.
Oh, sorry, yeah, I was wrong. 248 on that one.
Oh, okay. 248.98, did you okay, we got an agreement now. Okay, super, and it's in billions of dollars, so we'll put that down, okay? So, that's our first example of integration, right? So I think, like, adding that one back when it's power rule, adding that one back really gives us a hint, right? What to do with that coefficient, so. Let's try this one. Okay, this only has two terms. It's actually a little bit easier than the last one. So we have total expenditures in a country in billions of dollars are, and again, increasing at a rate of, right? Remember that rate of change, increasing or decreasing? So it tells us that this function is the derivative. It says again, x corresponds to the year 2000. And it tells us total expenditures were 1,584.6 in 2002, right? Again, that's our point, right? So our point will be 2 for 2002 and 1,584.6, yeah? It says find the function that gives the total expenditures x after 2000. And then find out what the total expenditures are, or what will they be in 2019. So it was a prediction or an extrapolation, yeah? Okay, so we take this function, right? And again, think about the two terms, they're both power rule. We found the derivative using power rule. So for 10.24x, right, we would square the x, which tells us that 2 is what some number was multiplied by to get 10.24. So we divide by 2. Yeah? Okay. 87.36. Right? That was with an x to the 0 or 1. Now we're adding 1. So we have x plus c, right? Tidy it up by simplifying that coefficient, 5.12 x squared plus 87.36x plus c, right? And then we take 2 and we substitute that value in for the x values, and the 1,584 we substitute for the f at x, or the f at 2. Yeah? Right? So Kevin, are you good with this? Where you do the calculations on the right and you subtract those values from the constant on the left, on the other side of the equality, and then we'll get our value of c. 1,388. 88.86. Anyone?
Yeah. I agree.
Okay. I'll wait. We have two in agreement.
Oh, sorry, it's 1,389 now. Yeah.
Okay.
89
All right, good. 89.40. Yeah, okay, super. Oops. I don't know where the error entered in, but anyway, that's our constant. So we can put that function back together with the constant in place. 5.12 x squared plus 87.36 x plus 1,389.4. And then it asks us, let me see here, to find the total expenditures in 2019. So we evaluate at F is 19, yeah? Yep, so in 2019, what were the total expenditures in billions? Wouldn't this have been terrifying in week one? But now it's like, we're cool. Look how far you've come, right? Are you so proud? Sorry? $4,897.56 billion. Anyone confirm? Okay, got a couple. Yeah, okay.
4897.
Beautiful. Okay. Right? You'd be, oh my goodness, what's happening? Yeah. It's amazing. It always happens, the evolution of the math student. All right, so you know how we start off easy and then it gets harder?
No.
It doesn't actually. It doesn't get that much harder, honestly. So remember I said we'd be looking at power rule and exponential rule. I think the next one we're doing is an exponential rule question. And I'm going to remind you that anytime you have an e function, remember the derivative of e to the ax, the derivative is a, e to the ax. So you just bring that coefficient of the exponent down, becomes the coefficient of the whole term, and then you just repeat the e to the ax term, yeah, or that part of it, yeah? And so in this case, because we're integrating, that means we're going backwards. We have a derivative, and we're going to go backwards and find the original function, yeah? So instead of multiplying by a, we're going to take that coefficient and divide by a, right? Whatever the a value is. So we have this question. It's the population of a country. It was 5.625 million in 1990. Okay, so that gives us a kind of a baseline, or that point we need. It says the approximate growth rate of the country's population is given by this function. I'll make it bigger so you can see all those decimals. But where t equals 0 corresponds to 1990. Okay, so here's our information. We see it's an e function. Our baseline year is 1990, so we've really got to pay attention to that. We get so used to it being 2000. And we also are told that in 1990, the baseline year. So when when t is 0, right? F at t is 5.625. And we know it says it's a growth rate function. So that is the derivative and we're going backwards. Yeah? Okay, I'm going to make it bigger. Does that help?
Yeah.
Yeah, okay. So I have f at t is equal to 0.12054375 times e raised to the power of 0.02143 t, right? Okay, so that is the a e to the ax, right? That's the derivative. So this is the a part, right? 0.02143. So we divide 0.12054375 by that coefficient of x. So this is what that looks like. Original function. Divide that by the coefficient of x. And then you repeat that. Right? And don't forget, plus c, because we're still looking for that definite integral. Yeah? Okay. So don't be alarmed, just follow the math. Right? What happens when you divide those two numbers? What do we get? Yeah, okay. 5.625. Okay. All right, so that looks familiar. Okay. So now we pull that point, so we know what the constant is. Yep. Go ahead.
Sorry, never mind. I was thinking it was I didn't see the
So the constant we were given was in 1990, which is t is 0, and we had 5.625. Okay, again, follow the math step by step and see what happens. Okay, right? Okay, so what do we know about e, or variable raised to the power of 0? 1, okay. Good. Remember that from our earlier days? So if this is equal to 1, right, then we have 5.625 times 1 plus c. Okay. On the right side of the equality, they're not multiplied, right? They're added. Right? 5.625 is a term and c is a term. So we multiply 5.625 from both sides. Right? So what's the constant in this case? Okay, 0, right, 0. I know it almost seems like, wait, can it be 0? Really? Can it?
So we're multiplying?
Just subtracting.
Oh, subtract.
5.625, I've said it, they're not multiplied, so you're just subtracting, so that, yeah. So let's put our function back together, now that we know that the constant's 0, right? 5.625 e to the 0.02143 t. Yeah? Okay. And it says, find the country's population in 2015. Okay. So we gotta go back, critical thinking. T was 0 for 1990, right? So what is the T, or the value of T, for 2015? It's 25, right? 2015 minus 1990, it's 25. Okay. So this is going to be great practice for you to remember how to use your E to the X button and the order of operations. It's a good little refresher. And so what's the population in 2015?
Is it 9.61?
Is it 9.61? Okay. I'm going to put the little squiggly equal sign, the approximate sign. Remember, because our E has all of those non-terminating decimals, so depending on how many are there. Yeah, so 9.612 maybe?
Mm-hmm.
Yeah?
Yeah, I just went to 9.61.
Yep, perfect. Yeah. And it's in millions,
Yeah.
says the question, so, yeah. Got that? Yep.
When you're going backwards, is the original function always a capital F?
Well, you see that the derivatives don't have the apostrophe, and so I give it a different one just to kind of denote that it's different. Yeah. You'll also see questions where it'll say MR at X, so marginal revenue at X, so you know. Some will have an apostrophe, or some will have that alphabet soup, right? Like the DX, TY, right? So I just do it so I make it look different. Yeah. But that's a good question. Okay, we'll do one more as an example, because this one does not challenge us a little bit, but just reminds us of how we can be flexible with our exponents. And this doesn't come in a context. It's literally, a very, like a basic calculation. It says find the cost function for the marginal cost function, right? So that's the function, and then marginal cost will be the derivative. And interestingly, in this case, it has the capital F, but it has the apostrophe, yeah. So it tells us. And I think, well, the reason maybe there is it's less in context, right? It's more like, here's the derivative function, integrate. So we have f prime at x is equal to minus 30 divided by e to the 0.04x plus 200, okay? And it also tells us 6 units cost $2,000. So what's that there for? Yeah, that's that x and y point. So we're going to use it later. So 6 and 2,000. We'll just put that aside, make it look like a point, so we're reminded to use that. Okay, so I like to give little asides, and you'll remember when we were working in the beginning with our powers and our square roots and all that, when we had an exponent 1 over x squared, where the x squared or any square or any cube term was in the denominator, we could give it a negative exponent and bring it up to the numerator. And that made finding the derivative with power rule easy. Well, turns out it also makes it easier to integrate, right? So we can remember that. And it might be useful for this question. Remember, we don't have, we're not going to be working with integrating quotient rules, so what else can we do to help us? Okay, so the first thing I would do is rewrite that function, or that derivative, sorry, with with that negative exponent. So negative 0.04x, yeah? Plus 200. Okay, so now we can recall again e to the ax as a function. The derivative is ae to the ax, right? And of course, the 200, well, that's going to be power rule, like we've done in the first couple of examples, yeah? Okay. So we're finding the original function. Minus 30 resulted from some number times the a part, the a coefficient. So to reverse that, we divide by whatever the a value is. In this case, it's negative 0.04. So negative 30 divided by negative 0.04. And then remember, we just repeat the e part. Yeah? 200 used to be 200x in the original function, right? Plus c. Okay. So I would tidy up that that division. So minus 30 divided by minus 0.04.
750.
Okay. 750. Did you do that in your head?
Oh,
Oh. I was like, holy cow, that's good. Didn't see your calculator. Okay. And then we go back and we use that point we were given, whatever that was. Let's see. 6 units, so x is 6 and f at 6 is 2,000. Remember that? Okay. We isolate for C. Still not working.
I'm just gonna have to go custom.
Are you locked out of other classrooms you're
I
supposed
go
to be
into
in?
every classroom. It
Oh,
happens
dear.
to other students too.
Uh-oh, well, you have to get that fixed. Okay, so what's our constant value?
$210.03.
Okay, anyone confirm? Yeah, okay, I see a nod back there. 210.03, so now that's our constant. We put that function back together. Okay, here we are. And now we're able to use it if we were given another part where we said find the cost at a certain number of x, right? Okay.
I got it wrong.
Oh, okay. Did you remember that it's negative 0.04?
Yeah.
Yeah?
Oh, I think I did that correct. Maybe it's
Okay.
a bunch. Maybe I messed up the decimal place.
And remember, it's e. You put your brackets negative 0.04 times your number, and then raise that to e to the x. This will be just a reminder how your calculator wants to receive the information, right? Alrighty. Did you get it? Yay! Okay. Questions so far? Anything? We're good. Integration's not so bad, right? When you get to that comfort level where you know how to do power roll, the E rule, rolling it back is, you know, seems to make sense, believe it or not. So, all right, good. I won't do this question, I think. Although, okay, I'll outline how you do it. First thing is, this is a marginal revenue function, right? R prime at X, it tells you. And it says find the revenue function, so you integrate, right? Now, if you don't sell anything, do you get any money? Right. 0 sold, 0 revenue. So there is no constant in a revenue function. You've probably noticed that time and again, or you haven't noticed it, but it's a linear function, right? We'd have well, if we had a linear function, remember we've had some revenue functions like, you know, 37x. All that means is every X costs $37, but there's no C because, again, if you don't sell anything, you don't have a revenue, right? So, so we don't have to worry about that as we would integrate this to a X cubed term. But I wanted to point out this as well because I think this hobbled us a little bit in the quiz 3, right? That relationship between the price demand function or the supply and revenue function. So when we get the revenue function, and it says find the price per item when 50 are sold, you're taking that revenue function and dividing by the X in order to get that price demand function, right? So hopefully if you see this again, you'll know that that's that step or that relationship. Yeah?
So where would we put the 50 in replacement of X?
So you would find the revenue function, which is 0.12 times 3 x cubed minus 0.02 x squared over 2, right? Plus 120x, right? And whatever that would be, so 0.04, I think, x cubed minus 0.01 x squared plus 120x. Then we divide by x, right? 0.04 x squared minus 0.01 x plus 120. That's going to be that price demand function. And then you would solve for 50. So when the price is 50, right, what's the demand? Yeah. It looks easy, goes so fast, but there's quite a bit of thought into it, right? It's like, what are we finding, and then what are we... It's like those questions we did earlier with the average cost and the marginal average cost. Like, it takes a bit of thought, and you've got to be... you've really got to think through the question. So, okay, so, okay, I won't do this one. I'm going to add. I want to point out the math notation, but don't be alarmed at it. Okay. So, but of course, we have to have fancy math notation, and that's when you see this business. You see the long, stretchy S. Have you come across it yet in your work? And then you see A and B, and then you see f at x dx, and there we have our alphabet soup, right? So what does this mean? The stretchy S just means to integrate. That's it. And integrate this derivative. Remember, dx represents derivative, right? So you're integrating whatever this function is that you're given and evaluating it between x as A and x as B. That's it. So don't get alarmed at all the weird notation. It literally just means integrate and evaluate, and you'll get your value. Yeah? Okay, blank page. Okay. So we've done quite a few examples of integration. Now I'm going to show you the first of the applications of the integration process. And it's called the fundamental theorem of calculus, but fundamental, and we're in week 13, right? But it is a way of utilizing integration. So essentially what it says, and it's also referred to as the area under the curve. Okay. So what does that exactly mean? So if you have a derivative curve, for example, if you take enough slices of the area under this curve along the axes, right, equal lengths of slice, and you take them smaller and smaller and smaller, the area under the curve will actually represent a value depending on what that derivative or that curve represents. The two most common things that we would see, again, this is all about business applications, you know, right? So the two most common applications we'll have is population distribution. Okay, so that's one. And energy consumption. Okay, so what the heck does that mean, and how are we going to use this? So think about the population of a city, okay, Mississauga. You could say, well, you know, there's so many people who are aged 0 to 1. How many people aged 1 to 2, 3 to 2 to 3, 3 to 4, 60 to 61, so on and so forth, right? And if you took those populations and graphed them, right, you would get an area distribution like what we've seen here, right? So it may be that peak at the top, maybe that's whatever the highest number of population. Maybe it's 37. Maybe the most people who live in Mississauga are 37 years old. I don't know, right? So that's how the age of the population is distributed, okay? So when we take these little teeny tiny slices out, we can actually determine the population of people that are that age, or the total population. So from population distribution, we can determine total population, okay? And at this point, I usually like to say this is the point where marketing students can, you know, see themselves in this. For example, what if you are starting a new business and you think, okay, well, I'm going to start a dog walking business. You want to know, are the people living in this community going to be good clients for your business? So who's the most likely to need a dog walker? Well, you know, people who are in the peak of their earning years, they go to work, they got the dog, they got the COVID dog, now they go back to class or to work, they need someone to walk the dog. So how many people are in that age group, right? If you want a diaper cleaning service, well, you're not going to go and launch your business in a retirement community where there's likely to be no babies being born, right? Ice cream store, well, everyone loves ice cream, so you're good. You've got the whole demographic. You see how it applies? So it's like looking at your population, using this population distribution to determine if you've got a good market, okay? So energy consumption is kind of along the same lines. Maybe it's per year, maybe it's per month. I literally get my energy bill, my hydroelectricity or my heating gas bill, and it says, well, where was your usage? And it shows you an energy consumption graph. So I could determine, oh, well, you know, and this is literally what I see, we're using gas and electricity to light our home because it's darker now. So you see that the energy use goes up in the winter months. And then you see the water use go down because you're not watering the lawn or the grass, like the plants, right? The reverse is true in the summer. Don't have as many lights on, you don't have gas to heat your house. Well, maybe you have air conditioning and so on. But energy consumption, the area under the curve would be the actual energy used in a period of time, right? So why would that be useful in a business setting? Again, maybe you're using some energy saving measures at your place of employment. Maybe you've got those lights, the lights only go on when someone moves in the room, right? And so now you're going to monitor your energy consumption, yeah? So that's, again, where you'd look at the area under the curve. So how do we get from derivative to the function? Integrate the function, right? So we integrate the function, and then we find the area between 2 points. And I'll show you what that looks like. And we gotta go back. If I looked at this graph again and I said, okay, well, I want to know how many people are between 30 and 40, if this was a population distribution, I would literally take the points 30 and 40, and I would substitute them into the original function and subtract or find the absolute value, right? It's an area, so it's a positive value. And that would tell me how many people are between the ages of 30 and 40 in this population. Okay? Let's go and into function. Okay, so here's a function, and it says that this is the marginal revenue function. It's measured in years, X years, and it is given in hundreds of dollars per year. Okay, so we know this is the derivative. It says so. And it says find the total revenue. Okay, so that tells me that we go from the derivative to the integral, so we reverse, and then we evaluate between 2 points. Okay, so what are the 2 points? What's the A and the B? 0 and 10. Yeah, this is how it's going to be. This is how it could be shown within those parameters, right? Between 0 and 10. Okay, so we're going to integrate this marginal revenue function. Again, they're not going to be anything other than power rule or exponential rule. Okay, so we have the x cubed term used to be x to the 4th, right? So that tells us that we divide that coefficient by 4. X squared used to be x cubed in the original function. X squared. Yeah? Now, do we need the constant here? Do we have a point on the function to tell us what that, or to help us find the constant? We're not given it, so it's kind of a clue that we may not need to find C, and this is why. Because we're evaluating this function at some point, like A, and we're subtracting the value of that function at B. So essentially, you might have, terms, blah, 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 plus C, minus, blah, 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 plus C. So you can see that we are subtracting the C minus C. So we don't need to know it. It'll be subtracted away in this case. Yeah? So our revenue function have 0.0175 x to the 4th minus 0.2 x cubed plus 2 divided by 2 is 1, so that's x squared. Yeah? Okay. So that's the squiggly line, f at x dx, and now the evaluation part. And I think we were asked to evaluate from 0 to 10, yeah? So r at 10 minus r at 0, which is cool. Each of the terms has an x in it, so each of the terms will be 0. So in this case, we have a little bit less work to do. Whoops, yep, there we are. So what was the total revenue between year 0 and year 10?
$75.
75, yeah? People are nodding, yeah, seems reasonable. 75, and wait, it's 7,500, right? So we can multiply by 100 there, and be 7,500, yeah? That was just given in the question, yeah? In hundreds of dollars. Did you get that, 75?
No, I got 73.
Oh. Let's see. Have I missed a sign somewhere? No. Did you get 75? You got 75?
Plus 75?
Yeah,
Yeah.
with 3. Let's try it again, Kev. Okay, so I guess that's a third business use. Population, distribution, energy consumption, and marginal revenue, yeah. And so that revenue would be kind of year over year, what's your revenue, and then what's your total revenue over that period of time? Like how's your revenue changing year over year,
I
and
did
then,
the second time 75.
you got 75? Okay,
Yeah.
all right. That back, you okay? Yeah? All right. There's going to be some, oops, sorry. Okay. Okay, let's have a look at this question. It is looking at the rate of residential electricity consumption. So again, all of those words are in there, consumption and rate. So we're looking at how much electricity is used over time, right? And it says X is 0 for 1990. Again, it doesn't, like the R at X really doesn't tell you it's a derivative. What tells you it's a derivative is the words in the question, right? And it says find the total consumption of electricity from 1997 to 2006. So those are the parameters. Those are the values, right? At the bottom and top of the stretchy S. So 1990 to 2006, 16 years, yeah? And then 97, like that, yeah? Of the integral. So don't forget, before you start substituting those values in, you've got to integrate that function.
So the top one always goes, the higher value always goes up.
Yeah. But when you get the answer, like it's the absolute value of that answer. So it's the positive value, it's the area, right? So I don't think you teach absolute value in high school math anymore. I think they dumped that. Absolute value.
I don't
this?
think I've ever heard that in high school when I was
Yeah.
changed that.
So it just means that if it's the absolute value of -5 is 5. It's like the value without the sign, so. Yeah. Okay, so let's integrate that. And again, e to the ax, you want to know those numbers there. Can I make it bigger? I know. Plus, it's kind of blurry with the lights on and the. All right. So here, I don't know. Should I put like a little r to denote we're going backwards? I don't know. 924.8, and we're dividing by the a part of that. Hey, hi. Come in. Okay.
Sorry, I couldn't help.
How are you? I'm good. I'm recording the lesson for 6 students just in case.
Hi, everybody.
Calculus, come on in, Shadi.
Enjoy calculus. I know.
Look at them, they're just eating it up. Thank you.
Having a great time.
Okay, so we're going to divide by that a value, right? And then we just repeat that 0.0275x, yeah? And so what is that? Zero point 0.0275.
33,629.09.
Yeah, about that.
Okay, okay. I might just leave it without decimals. I don't know, but that's fine. You can put them in.
Okay.
Okay, so then we evaluate that function at 16. We evaluate that function at 7, and we find, you know, again, the absolute value. It's a positive value of that. Because again, we're looking at energy consumption. We can't have negative energy use, right? Maybe I should just record all of the lessons this week for all of the students. Because everyone's all, right? As everyone's kind of overwhelmed. Don't forget to take care of yourself. Get some good sleep, good food.
Sorry?
Take care of yourself this week and next week.
Next week.
Get some sleep, get some food, walk in nature.
Next week I have a few exams.
Yep,
This
next
I only
week.
have one thing.
Does anyone have more than one exam in a day next week, or is it spread out pretty well?
Mine's spread out. pretty
Spread
well.
out, yeah.
Tuesday this week and then next week, Monday, Wednesday.
Oh, that's good. Yep.
That's about it. And then I have a quiz, which is it's elective. It's all history.
Mm.
Okay, so you're probably gonna learn though.
Who, me?
All the professors, I remember one time the professor was like, you gotta mark a lot.
Yep. I still have my same day guarantee. I'll mark the finals the night you write them, or the day you write them. So you'll know. And then I won't be looking at the my math lab grades until, right? I've given you that extra time, which means I'm gonna be looking at them later in the week, so. Grades are due the Tuesday of, so it's 16, 17, 18, 20th of December? 20th. I never do it till the last minute, because you know what happens, right? The server goes down or something. But, yeah, but the My Math Lab I'll look at December 16th, so. Okay, what's the energy use between 1997 and 2016?
$11,448.37.
11,448
48 and 37.
37.
I was using the decimals though.
Oh, yeah, you were. Yeah. Okay, so ish. I wasn't using decimals. I got 39, so 37, 38, around there. Yeah. And again, it's an E term, so it depends on how many decimals in the E you use as well, right? And it's billions of, and energy is measured in kilowatt hours. So you'll see that 11,448 billion kilowatt hours. Yeah. Has anyone been to the old electrical generating station in Niagara Falls, where you go and you see the old equipment and then you can go out kind of like
Up
under the
the
falls? Yeah.
Yeah,
Yeah.
when first we went with our cousins.
Was it cool?
Yeah, it was pretty cool. And my dad's like, such a waste of money, but like it was pretty.
Don't tell me that. I think I'm gonna go this Sunday. We're going
Yeah, I
away
think
for the
it's
weekend.
worth it in my opinion. Like you just go under, then you get to go like under the actual falls, and you get to take pictures, and you get to come back, and there's like historic stuff.
Cool.
Under there, you get to see, and there's like facts on the side
Yeah.
each time, and then you come out to the exit.
Everybody wants to see the falls when they visit, hey?
Mhm.
Yeah.
I have a friend who has a Brazilian student staying with her doing a semester in Nova Scotia. And I messaged her the other day and I just said, so do you think Larissa would like to come and see Toronto? I said I'd be happy to host her here. But anyway,
Mhm.
apparently she's been here already. So, because I love the excuse to show people around, like Toronto, Niagara Falls, and, you know, cool stuff, cool kids. I don't know. Anyway. Okay, does that make sense? Integrate, evaluate, all the information you need. Look for the words, which direction you're going. Are you given a rate function? Are you given the original function? Yeah? Okay. So here's a two-part integral. This is cool. We've done quite a bit. Are we okay? Keeping up? Is that, yeah? Okay. So this refers to what was the 2010 census. So does everyone know what a census is and what its purpose is? Census, yeah. So we just did a long census. We have a short census and then a long form census. And the long census was just done in Canada. And it basically gathers information about, you know, Canadians, right? What do you do? How old are you? Where do you live? What services do you use? And it basically says, well, what services should the government provide in your area based on the age distribution of your population, right? How many schools should we count on, right? So the census in 2010 produced this age distribution function, right? Which basically says how were the ages of people distributed over the whole population. X is the age in years, and F at X gives the number of people in thousands who are that age. The population of an age group in the region can be found by integrating the function and then evaluating that interval over the age group. Okay, so again, this first one, it says find and interpret. So you've got the long stretchy S, 90 at the top, 0 at the bottom, F at X dx. So that means integrate, right, the stretchy S, the derivative, and evaluate between 90 and 0. That's all that means. So we take that function, and, you know, we're going to look at the function and say, okay, well, that's a power rule, 3 terms. We've got this. We know how to do this, right? And then you evaluate, or integrate, sorry. So the x squared used to be an x cubed in its past life in the function, right? So that means we divide that coefficient by 3. Then we take the next term, the x used to be an x squared. So we divide that coefficient by 2. And then 5,123 used to be 5,123x in the original function. Yeah? So we can simplify. Yeah. And then that's that first step. We've integrated and now we evaluate. And remember, we were looking for the population of people who are from 0 to 90 years old, right? So f at 90 minus f at 0. We evaluate at 90, we evaluate at 0, and we find, well, essentially the absolute value, or that value of number of people. Okay? And then minus 0, right? Because f at 0, when every term has an x in it, that makes every term 0. Yeah? Okay, so what was the population of folks? So 508,860?
Yeah.
Okay. Anyone confirm? So a smaller city of 500,000. Yeah. Okay, so that's your potential demographic or client base if you're going to start a business in a very broad industry, like, well, ice cream or something everybody loves to have and take part in. So the second question, or the second part of the question says, just let me erase this a little bit. It says, integrate and evaluate between 40 and 30, right? So now we're looking for a narrow band, right? A narrow band under the curve. We're looking for a smaller demographic, right? Okay? All right. See you next week. Sorry?
Work time.
No worries. I recorded this so you can see the end of it. You're welcome. See you next week. So if we're looking for people who are between the ages of 30 and 40, let's think about what our value might be, right? So from 0 to 90, and we're looking for a 10-year span. So maybe we're looking for something that's a 9th or a 10th of that value, right? So that gives us a ballpark. So we don't get some wild number and go, that must be right. We have an idea. Well, you know what happens. So let's go back. We have negative 0.19 times 40 cubed plus 23 times 40 squared.
Doesn't matter if we do 30 minus 40 or 40 minus 30.
It doesn't really, but yeah, but if you get a negative number, you know you've got to take the value, not the sign.
Not the sign, okay.
Yeah, yeah. So I always try and position it that I'll
You
get the
don't-
positive value, yeah. Okay, so that's in big brackets. Whoops, and then subtract. And I might have to write this on another line. Be really careful of your signs, right? Don't do all that work and then get overconfident. Make sure you've got those signs right. So because x isn't a zero value, you've got to do both the calculations, right? Anyone there yet? For students at home on the recording, it's a great time to stop the recording and get the answer and then proceed, right? It's a great way to practice. Yeah, in all those YouTube videos. See if you know the next step.
A lot of students see too.
I thought there might be.
Oh,
I got an email from Ryan, he was sick, so I thought others might be. Plus you can use it to review,
I'll review.
just in case. Because you're probably thinking about other stuff. Hmm?
Negative 42,000.
So 42,000, you think? Yeah? 42,116? Anyone?
I got 60,300.
Okay. 60,300? Anyone? You got that? 2? Brian, 2? Yeah, okay. So again, we got to think, does it make sense, right? That number sense. Does it make sense? So we had 508,860 covered that whole age span from 0 to 90. So let's say a 10th of that or a 9th of that would be from 30 to 40, sorry. So what is 508,860 divided by 9-ish? My calculator. So 508,860 divided by 9 is about a little over 56,000. So that makes sense, right? We're in the ballpark. That makes good sense. Yeah? Okay. Did you get that? Okay, 60,300. Did you see what went wrong? Okay, good, all right. Okay, so that brings us to simple integration and then area under the curve. And those are just examples of the kind of questions you'll see. There'll be some integration questions on the final exam, and there will be an area under the curve question, right? Okay, so the last thing we have to do, which literally wraps up all of the learning outcomes for your course, yay Monday, thank you so much, is consumers and producers surplus. So when we think about what those words mean, consumers and producers surplus, we think about surplus, right? And I don't know if you've heard that word before, but surplus is used to mean something extra, right? Something left over. So, I mean, the most common usage I've had in my life, my father was in the military, is army surplus. When they sell off the boots and the jackets and all the stuff from the army, and they sell it cheap, and students buy it and they think it's fun and cool to wear, you know, right? So surplus means extra, and you're selling it off. So when we look at producers or consumers surplus, what does that mean, right? So producer surplus just means the extra that a producer would get from selling something at a value or a cost higher than what they anticipated, right? Consumers mean, yay, we get a deal and we spend less than we anticipated. So we have a surplus of money. We've kept more than we anticipated. When does it happen? When does a producer or a consumer get a surplus? Okay, so I don't know, have you heard this? Have you spoken about this in an economics class, for example?
I think with
Have you heard
consumers,
that?
like you said, they get more than, like maybe if there's like let's say I've seen a lot of clothing shops when they have more clothing than you
Yeah.
need around clearance and stuff.
Yeah.
Like,
More clothing than they need in a store, and they sell it off. So what does that mean? That means an imbalance in the supply and demand, right? So, I mean, a classic example is Apple products, right? Hey, we got the new Apple iPhone, and we're gonna sell it, and then there's lineups out the door, and then they're all sold out, and then you see the price in the aftermarket. Somebody goes in and buys a bunch, and then they mark up the price when they're sold out, and they resell them, right? So that's an imbalance in the marketplace between demand of this iPhone and the supply of the iPhone. Well, it can be purposefully rigged, right? Where I'm gonna make fewer products than I can sell, and look how much more money I'll make, right? So what if the supply is greater than the demand, right? So you see that all the time where someone thinks they got a great idea, and then they make a bunch of stuff, and then people are like, yeah, I'm not that interested in it, and they don't sell what they anticipate, so they have to put it in the Dollarama or Treasure Chest, or put it on sale or whatever, right, to get rid of it. So that's where the imbalance occurs. Okay, so what does that mean? We've talked about, and I'm going to close this up and open up a new